Hello and welcome to day 12 of my Advent of Code series for the year 2020. If you've missed any of the previous episodes and you want to go ahead and check those out, then check out the playlist linked right up here, and be sure to get subscribed and turn on notifications for my channel so you don't miss any future videos. So today we are going to look at rain risk. So the idea here is our ferry, we're on it, and it is experiencing some bad weather and we need to get to safety. And we have navigation instructions to safety, but the navigation computer is broken, so we need to figure out where those are sending us. This is just another sort of rule following one like we had early on in Advent of Code, which is not that interesting, but it's fine. So pretty much north, south, east, and west all tell us to move in that direction by the given value. Left means to turn left by that many degrees, right means to turn right by that many degrees, and F means to move forward in the direction that we are facing. So we're given a list of instructions, and we need to handle them like that, and we start off by facing east. So this is a pretty easy one. You just need to return the Manhattan distance from your starting location at the end. So I recommend you go ahead and give this a try, and we're going to jump into my code right now. So the way that I did this is first we just read in our instructions, and then those get passed to part one. So I initialize a position marker, which has our XY position, or our vertical position first, and then our left-right position, our horizontal position later. So then I initialized face as starting at 90 degrees to signify east, and that's the direction that we are currently facing. So each of the cardinal directions map to something in this DERS dictionary right up here. So you'll see I have north means going up and not at all to the side, east means going right and not at all up or down, south means going down and not at all side to side, and west means going left and not at all up and down. So then we have our rotations and what those map to, which map to the same things except for north is 0 degrees, east is 90 degrees, south is 180 degrees, and west is 270 degrees. So that's how that works. So what we do is we loop through our instructions. Our direction is the first character in our instruction, and the value is the int representation of the rest of it. So then what we do is if we have a forward as our instruction, then we are going to go ahead and set two things called y and x. I just did this here so that it would look a little bit cleaner. Two rotations, which is this dictionary up here, sub face, so if we're facing 90 degrees, it'll be 0, 1, and we just add into our positions whatever these things are, multiplied by the value of how many times we're supposed to do it. So then moving down to left and right, if we are turning left, then we are going to go what we are currently facing minus the value of however far we're going to turn, and then we just modulus that by 360 to put it in the bounds of 0 to 270 here essentially. Because it's by 90. So once we get that in bounds, then we'll have a rotation that matches this because all of the rotations are divisible by 90, which makes this nice and easy. And if we're going right, we do the same thing, except we add those values together because if you think of turning right is essentially going clockwise and it's going to add to your degrees, and left is going the opposite way. So then otherwise, that means we will have a cardinal direction value of northeast, south, or west. So we do a similar thing to what we do in forward, except for we look up in our directions instead of in our rotations. So then at the end, once we loop through all of those instructions, we simply return the absolute value of each of the parts of our position, and that will give us our Manhattan distance, and that is our solution. So after that, we can jump down to part two. So for part two, we noticed that we actually got the directions completely wrong, and what the things that are north, east, south, and west are talking about is moving a waypoint that is some amount away from the ship to a different position near the ship. Left and right mean to rotate the waypoint around the ship. So if you think of the ship in the middle and the waypoint here, if we were to rotate it left, then it would go this way. If we were to rotate it right, it would go this way. So that's rotating the waypoint about the ship. And then finally, F means moving to the waypoint several times, however many times it specifies. So the waypoint starts 10 units east and 1 unit north from the ship, and the waypoint is always relative to the ship, so even when we move to the waypoint stays whatever amount away it was before. So it goes through an example here, and at the end we just need to return our Manhattan distance. So again, I recommend you go ahead and give this problem a try. It's not too much harder than the last one. And we will jump into my code right about now. So I was very tempted to go with a linear algebra based approach because you could switch these all to just transformation matrices, but that is just way too, I don't know, it's too much for this problem really, and I wanted to keep it simple and explainable. So I ended up writing two functions here. We have the actual part 2 function, which looks very similar to the part 1 function, and I added one called rotate waypoint. So what rotate waypoint does is it takes in a waypoint and a value, and it rotates the waypoint about the about the ship, however many it is supposed to. So the waypoint, how I have it initialized here, is just always going to be how far it is relative to the ship, rather than being an exact location, because I just found that's way easier and makes way more sense. So then what we do is, if it's 90, then the waypoint ends up switching around so that the first element of the waypoint is the negative value of the second part, and the second part is whatever the first part was. If we rotate 180, you can think of that as just reflecting across the ship, so we're just going to have the negative of both of those values, and 270 is essentially doing 90 in reverse. So that's pretty much it for that. It's not the most difficult thing to understand, that rotate waypoint. So then we move on to the actual part 2 function here. So instead of just instantiating the ship's position, I instantiate both the ship's position and the waypoint's position. So then as we are looping through our instructions, we break it down the same way as we did before. So then we have our same cases that we're looking for. If it's equal to forward, then we set y and x, instead of being the values that we set before. Based on our dictionary, we set it to the parts of the waypoint, and we just move to the waypoint however many times. If it's left, then what we do is we go ahead and rotate about the negative of whatever value it is, modulus 360, just to get it back into range. You could also break this down into a more exact thing and just say 90 goes to 270, whatever. You could just do it with one subtraction, but I determined this looked a bit more readable. So essentially we're just rotating backwards from what the rotate waypoint thing does, because the negative, it's essentially the negative values of those angles. And then for right, we just rotate waypoint directly, the amount in the value. And then if we have a cardinal direction, then we break down that cardinal direction based on our Dur's dictionary from before. And instead of adding it to our position of the ship, we add it to the position of the waypoint. And finally, we return the Manhattan value of the ship once we've looped through all of our instructions. So that's it for part 2. Today was just another sort of rule following one. Nothing super duper interesting in this week, or in this day, if you ask me. This week has definitely been the most interesting. But hopefully things will ramp up a bit again soon. I hope you enjoyed this video. If you did, leave a like and share it with anyone who you think might be interested. Be sure to get subscribed so you don't miss any future videos from me. And I will see you in the next one. Where is my... Goodbye.